Welcome to Unit 14, Video 5, Rate Laws. By the end of this video, you should understand what a rate law is and why it is necessary. You should know what the order of a reaction for a given reactant is and how to determine it given rate data. You should be able to calculate the rate constant from rate data. And you should be able to write a complete rate law given rate data. Recall that we saw in the last video that rate is not constant. As the concentration of reactants decreases, the rate of the reaction tends to slow down. Therefore, taking the average rate over the course of the entire experiment doesn't tell us much. Instead, we use something called a rate law. This is an equation that shows how the rate of the reaction depends on the concentration of reactants and products. In other words, we can calculate how fast the reaction is going at any point in the reaction if we know the concentration of reactants or products. For example, if we have a reaction of A plus B yielding C, we might have a rate law that looks something like this. Rate laws will always have this form. The variables in this rate law are as follows. K is the rate constant. X and Y refer to the order of the reaction with respect to each reactant. The order tells us how the concentration of each reactant affects the rate. K, X, and Y must be determined experimentally. You can't get these simply from looking at the reaction itself. You have to actually have experimental data in order to fill in K, X, and Y. Also important is that K is dependent on temperature. When you determine these values from experimental data, the value you determine for K is only good at the temperature at which you run the experiment. If you change the temperature, you need a different K value. In order to determine the rate law, we need to figure out exactly how the concentration of each reactant affects the overall rate. We do this by holding the concentration of all but one reactant constant and seeing how varying that reactant affects the rate. This is then repeated for each reactant. In other words, we would hold A constant and vary B repeatedly to see how the rate is affected, and then we would hold B constant and vary A repeatedly to see how the rate is affected. Again, this must be determined experimentally. There's no way to look at a reaction and know its rate law. The biggest thing that we need to determine when looking at rate data is the order of the reaction. Recall these were X and Y, the exponents for each of the reactants in our equation before. The reaction order describes the effect on the overall rate when the concentration of a given reactant is varied. We will look at three different possible orders: zero order, first order, and second order. There are plenty of others, but we're just going to look at these three in this class. The order can be different for each reactant. So if a reaction combines reactant A and reactant B, it might be, say, first order in A, but second order in B. A zero order reaction is a reaction in which varying the concentration of the reactant has no effect on the rate. So if you double the amount of that reactant, the rate does not change. A first order reactant is one that the change is directly proportional to the change in reactant concentration. In other words, if you double the concentration of that reactant, the rate will double. If you triple the concentration of that reactant, the rate will triple. And finally, a second order reactant is one where the rate change is proportional to the square of the change in reactant concentration. In other words, if you double the concentration of the reactant, the rate will quadruple. If you triple the concentration of the reactant, the rate will multiply by a factor of 9. We can follow 4 simple steps to determine a rate law. First, we determine the general form of the rate law. We'll go through each of these steps for a reaction so you can see what I mean. Then we determine the order with respect to each reactant. Once we have these values, we can write the rate law expression. And finally, we can use experimental data to plug in and solve for K. Here's our first example. This is a simple decomposition reaction where we have 2 moles of N2O5 yielding 4 moles of NO2 and 1 mole of O2. Notice we've run 2 trials here. Since there's only one reactant, there's nothing to hold constant, so we just varied the concentration of N2O5. Step 1 told us to write the general form of the rate law. The general form of the rate law just fills in the reactants in the rate law, but doesn't fill in X, Y, or K. So here we would just write rate is equal to K times the concentration of the reactant raised to the power of X, X being the order, which we're going to determine in the next step. So that's our general form of the rate law. Next, we need to determine the order of the reaction. In order to do this, we need to compare two trials in which only one reactant is varied. Since there is only one reactant here, it's the only thing to vary, so let's look at these two trials. Notice from trial 2 to trial 1, the concentration has doubled. Notice also that the rate from trial 2 to trial 1 has doubled. Therefore, the concentration and the rate are directly proportional to one another. Since the rate doubles when the concentration of N2O5 doubles, the reaction is first order in N2O5. Therefore, we now know our order is 1 with respect to that reactant. So X is equal to 1. We can fill in that information to write our rate law expression. We now know that rate is equal to K times the concentration of N2O5 to the first power, which should make sense mathematically. If we raise the concentration of N2O5 to the first power, that means that doubling N2O5 will double the rate, tripling N2O5 will triple the rate, and so on and so forth. From there, I can plug in rate data and solve for K. Using my rate law expression, I can plug in data from the first trial, rate being equal to 5.4 times 10 to the negative 4th, and concentration being equal to 0.9. Solving for K, I get a value of 0.0006. Repeating this procedure for the second trial, I see that I get the same value for K. With nice clean data like this, our K value should be consistent. When you run these trials in a lab, however, it tends to be much messier, so we often have to take an average value for K, given many trials. Now let's look at a more complicated example. We're still going to do this one together. Notice this is more complicated because we have far more reactants. In our last example, we only had one reactant. Here we had 3. Therefore, we needed to run lots of trials in order to get combinations where we varied the concentration of each reactant while keeping the other 2 constant. For instance, if we look at trials 1 and 2, we see here that we varied BrO3- and held Br- and H+ constant. This allows us to see the result of varying BrO3 in a controlled experiment. Let's use this data to create our rate law following the steps we just learned. First, we're going to write the general form of our rate law, which is going to be rate is equal to K times the concentration of the first reactant, BrO3-, raised to some power, X, which we'll determine in a minute, times the concentration of Br-, raised to some power, Y, which we'll also determine in a minute, times the concentration of H+, raised to some power, Z, which we'll also determine in a minute. So there's our general form of our rate law. Now we need to determine order for each reactant. So let's start by trying to determine X. X is the order for BrO3, so we need to find 2 trials in which the concentration of BrO3 changes, but the concentration of the other 2 reactants remains constant. Looking at trials 1 and 2, we see that this is the case. Here, we've doubled BrO3-, and if we look at our rate, we see that our rate has also doubled. 8.0 times 10 to the negative 4th is the same as 0.0008, and 1.6 times 10 to the negative 3rd is the same as 0.0016. So it's easier when you write it this way to see that this is indeed double. Therefore, since our concentration is directly proportional to our rate, X is equal to 1. Turning now to Y, here we need to find 2 trials in which the concentration of Br- changes and the concentration of the other reactants remains the same. So take a second and see if you can figure out which 2 trials we should use here. If you said trials 2 and 3, you're correct. In trials 2 and 3, notice that BrO3 is constant and H plus is constant, but Br minus doubles. Looking at our rate, again, we see that the rate has doubled. Again, write it out in standard form if you need to see it. So we have 0.0016 and 0.0032. 16 and 16 is 32. Again, since we have a directly proportional relationship, our order for Br minus is 1, so y equals 1. Finally, Z is looking at H plus concentration and how it affects the rate of the reaction. So find two trials in which the concentration of H varies and the concentration of the other two reactants remains the same. If you said trial 1 and 4, you're correct. Notice that here, BrO3 remains constant, Br minus remains constant, but H2 doubles from trial 1 to trial 4. Taking a look at our rate in this case, however, from trial 1 to trial 4, it actually quadruples from 0.0008 to 0.0032. 8 times 4 is 32. Therefore, since our concentration is proportional to the square of our rate, then our order in this case must be 2. It's second order in Z. Using all this information, I can rewrite our rate law as rate is equal to K times BrO3 minus to the first times Br minus to the first times H plus to the second. This is our rate expression. This is what you'll most often be asked to find. From here, we can plug in values from any trial to calculate K. I'm going to choose trial 1. So our rate in trial 1 was 8.0 times 10 to the negative 4th. K is our unknown, or our x. BrO3 was 0.1 to the 1. Br was 0.1 to the 1. And H plus was 0.1 squared. Solving for K here, I find that it's equal to 8. That brings us to the end of this video. Let's review our goals. First, we looked at what a rate law is. It's a mathematical expression that relates rate to concentration at any point in the reaction, and why it's necessary. Recall that average rate is not very informative since rate changes over time. Then we looked at what the order of a reaction is for a given reactant. Recall that this tells us the effect of that particular reactant on the reaction rate. And we learned how to determine it from rate data by comparing two trials in which the concentration of one reactant is varied while the others are held constant. Then we learned to calculate the rate constant from rate data. This is K. We just plug in some rate data and solve for K. And then we learned how to write the rate law from rate data by filling in our K value and our orders for our reaction.